Right, we begin now with Keplers Laws of Period. So named, we know that Newton's three laws are named after Sir Isaac Newton, but another very important person around at the same date and age of Newton himself is Johannes Kepler. Johannes is just the German for John, so it's just John Kepler. And he comes up with three laws of planetary motion, which they're all based on observation and measurement. So he doesn't come up with three laws based on mathematics like Isaac Newton did. These are three laws based on measurement. That's the reason why this painting here has him holding dividers, which are the other instruments in your geometry set, because he did a meticulous measurement of the night sky to come up with his three laws. Now we only have to do one of the three laws, which is the third law, but just to make sure that we complete the idea of what the laws are. The first law is the law of orbitals. You don't need to know these. The only one is the third law, and we'll go on to that in a few seconds. He realised that there was no circular paths in orbits. Orbits were ellipses. So his first law says that all orbits are ellipses where the sun, the earth, the planet going around the sun is one focus of an ellipse and the planet goes around the circumference of the ellipse. The second law says that in equal times, the planet that is orbiting the sun, because obviously there's only, in this time there was only the sun and there was only 5 planets, as the planet goes around from E to D here, it sweeps out an area, or what we call a elliptical sector. That elliptical sector has the same area if it's in equal time. So from A to J here, the planet would move from A to J in the same time as it goes from E to D, depending on making sure that they're the same area. Are we okay with that? The third law, which is what we're about to do, is called the law of periods. And he discovered that if you cube the radius, the orbital radius, now the orbital radius is called the mean orbital radius. And what I mean by that, because these are ellipses, that would be a radius, but when the planet is over here, that is also a radius. If you sum all the radiuses together, you get as many as you possibly can and divide it by the number of radiuses that you've measured, you get what we call the mean radius. So this is the mean radius. And the 5 or so planets, now he only knew of a few planets, he did not know anything about Neptune or Uranus, but he knew about all the other planets. He did not know much about the moons of Jupiter, even though Galileo had just discovered them. So he discovered that if you cube the radius and divide it by the square of the time taken for a planet to orbit the sun, it was always the same. It was a constant. And that was for all the planets in the solar system. Okay? So remember, he's not basing any of this work on mathematics, he's just simply basing it on what he knows as observation. So we have to derive this law of periods and do the mathematics that is behind it. So we start now with a circular orbit. Now remember, though Kepler says that all orbits must be elliptical, we know that one orbit is permissible. It is a circular orbit, and a circle is the very special form of the ellipse. Though we're about to do it for the circle, it will then be able to be applied to ellipses, as long as we talk about mean radiuses. Okay, so here is the sun, or the central object. So here we are right in the centre, here is our central object. Now, the central object is going to be given as we've always done, the letter capital M. So for the Earth going around the Sun, what is the central object of our orbit? The Sun. For the Moon going around the Earth, what's the central object of its orbit? The Earth. For Io, which is going around Jupiter, the central object is Jupiter. Now, we have to realise that the central object is the most important thing in Kepler's law. The K value that we will derive is dependent upon what is the central object. So it will change if the central object changes. So, let's start there as our mass of the central object. Here is little m, the mass of the moving object, the thing in orbit. So that would be the mass of the Earth, if we're talking about the Sun, Earth, or it will be the mass of the Moon if we're talking about the Moon, Earth. Okay, we need to find our orbital velocity, and our orbital velocity will be given by the formula here. We've been using this quite significantly in our worksheets, haven't we? That velocity is distance over time. The velocity, the distance, is 2 pi r, where r is the radius of orbit. So it becomes 2 pi r over the period, which is t. And we are defining t as the time taken to make one complete orbit. Are we okay with that? A complete orbit is really what we call a year. So, but we have a tendency to only reserve the word year for Earth. Otherwise, we get confused with different years. So, if this was the Earth, then T would equal 365 days. If this was the T for Mercury, it would be 88 days and so on. Are we okay with that? So, there is the velocity of an object in orbit around any circular motioned orbit. Rightio. Now, last lesson, or the lesson before, we derived this formula. Does anyone recognise it? It's the orbital velocity formula. Good. And the orbital velocity formula was found by equating centripetal force and gravitational force. Okay? And I'm not going to rehash that. So if you're asked to read, you have to be able to actually get this formula up for the HSC. If you need to derive it, you can start here, at this point here, but you are best to be able to derive the whole thing. But I'm not going to redo that. So if you need to, go back and work out how to get that formula. So this is the orbital velocity, and we just worked out another way of working out my orbital velocity is 2 pi r on t. Okay, where t is a period. If these are both orbital velocities, what must they do to each other? They equate to each other. Now, just realise what is in this formula. This thing over here, that m is what? The mass of the central object of orbit, it's the capital M. The little m, which is the mass of the orbiting body, has already been cancelled. By getting this formula over here created, we've already cancelled the little m on both sides. Are we remembering that? So, we are at this point here, we're about to get Kepler's Law up. How would I solve this? What would I do to both sides? We're going to square it, and you get 4 pi squared r squared on t squared would equal capital G m on r. And the last thing we need to do to get Kepler's full law up is, we go back, we're going to quickly zip back, having a look at this slide here, the way that it's normally done or presented to us is radius cubed on t squared. So we need it in that form. So the best way for this to happen is that this radius down here goes up and the 4 pi squared here goes down. So rearranging that now, you get r cubed on t squared is equal to capital G m on 4 pi squared. Okay? Are we okay with how to equate those ones there? And in the blue book, you just have to do that in question 35. Okay. So that gives us the final equation for Kepler's law. Now, it's r cubed on t squared, that's the thing that I showed you before. But the other side, a few moments ago, you saw the letter what?
K.
K. Now, why is the other side a K? Well, the things which remain constant are G is 6.67 by 10 to the minus 11. 4 and pi are simply numbers. And M is the mass of the central object. Now, if we are talking about our solar system, so the solar system has the sun in the centre, and then it has Mercury, Venus, and say the Earth. What do Mercury, Venus, and Earth all share as the central object of their orbit? The sun, which would have its capital M. So for a whole series of a solar system, a whole series of bodies, this M stays the same. Is that making sense? So that K, where K equals capital G M on 4 pi squared, stays the same as long as we're all orbiting the same object. Are we okay with that? So this K is the same value as we would share if it was Jupiter. So if Jupiter's orbiting the sun, because Jupiter's orbiting the sun and that M stands for the sun, we would share the same K value as the sun, as Jupiter for the sun. However, it will change if the central object changes. So if we were talking about Io, so this time we're talking about Jupiter as a centre, and here is Io, which is the first moon, and then here is Callisto and Europa. Are they orbiting the sun? No. Now that it's a different orbital system, there is a different K. So for every central object of orbit, there is a different K. Are we okay with that? Okay. And the K value can change. R and T are traditionally, R is measured in metres and T in seconds. But if we were to do everything in kilometres and everything in hours, then this K over here can change quite okay, as long as everything in the entire solar system is measured in kilometres and hours. It will be still the same K. However, that's one of the things that we hate about physics formulas. They must always go with the three standard measures of metres, seconds and kilograms. So we should leave it as metres, seconds and kilograms. Is that clear? But it is a forgiving formula if you do use kilometres and hours. But you would have to change the G. Okay, so let's now use it. And this is the most commonly used formula in the HSC, which has a quite high failure rate. It's because people can't cope with cube roots and square roots and so on. Okay. The planet DNAB, just made up, as an orbital period of 20 days, determine its orbital radius, and we need to know what it's orbiting. So let's give a central mass. Let's say that it's orbiting the sun, and the sun is 2 by 10 to the power of 30 kilograms. Okay. So we're going to pretend there's a mythical planet going around our solar system called DNAB. Okay. So what is its orbital radius? So we've got r cubed on t squared is gm on 4 pi. Don't forget there's a little square there. There's the most common mistake, because a lot of people just say 4 pi. It's 4 pi squared. We want to find orbital radius which is this one up here. Now, a lot of people decide to put all of the values in first and then try to manipulate scientific notation. It's painful if you do that. The best way of doing it is to manipulate the formula first. Use the algebra to manipulate. We want this as the subject, the r cubed. So we're going to just get rid of the t squared by putting it up there. So the first thing we do is get rid of it, and it becomes t squared gm on 4 pi squared. Okay? A lot of people decide to put the numbers in first and then try to move the numbers. That's a bit hard. Okay, shoving in the numbers. The first thing we need to put in is t, and t in this case is given in days. So we're going to convert it firstly into to seconds. So it's 200 times 24 times 3,600. What's that, please? Have we got a value on that, please? 280,000. We agree? Okay. And so r cubed would equal 17,280,000 squared times g, which is 6.67 by 10 to the minus 11, times the mass of the central object, and this time it's the sun, because d nav is going around the sun, so it's 2 by 10 to the power of 30, all over 4 pi squared. Please, when you are setting this out, set it out fully as if you are sitting a maths exam. They will give you partial marks. They will mark this just like a maths exam. If you do something silly, you get the majority of your marks, and so on. So set it out, write in, do not write bald answers down. Has anyone got a value for the r cubed in this case, please? 0.009 by 10 to the power of? 33. Okay. I'm not going to ask if you've got a second on that. We now r cube it, so cube root it. And the cube root of the same value above is equal to
1.003 times 10 to the
10 to the 11. And this is, it's r, and we would be measured in metres. Okay, do we agree with that? Okay, you can see where the biggest problem with all this is. It's these powers, okay, which people forget. Are we okay with that? Right, so let's move to another example. This one here is determining the mass of the star. The three things that you need to be able to determine with this is R, T, and M. Okay? So this time it's the mass. So a planet has an orbital period of 90 days. So there is the letter T. It has a mean orbital radius of R there. And we need to find the capital M. Okay? So the first thing we're going to do is write down the formula. But since we need the mass, I'm going to write it in its reverse. So I'm going to write Gm on 4 pi squared equals R cubed on T squared. We want M by itself. Now, remember, it is easier to manipulate this equation before you put the numbers in. Okay. To get M by itself, that means that M would equal, well, the 4 pi squared comes up and the G goes down. So it equals 4 pi squared R cubed on GT squared. Okay. The last thing, which is a big source of error, is to put in values for R and T, which are not metric, which are not part of the SI system. So you can use the formula for days and kilometres, but that means you would have to find another value for G which accommodates that. Does that make sense? That's the only part about this formula which has to be taken into account. But we haven't got a G which is designed from kilometres and days, so I need to convert them. So T would equal 90 days times 24 hours times 3,600 seconds per hour. And r would equal, this is in kilometres, so adding 3 more zeros, I go to metres. And so it'll be 1.2 by 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 metres. I hope I counted correctly there. Shoving in the values, it's 4 pi squared times 1.2 by 10 to the 11 cubed, all over 6.67 by 10 to the minus 11 times whatever that thing up there, 90 times 24. I'm going to just put a question mark, and that is squared. Okay. Has we got a value for the t, please? 7 million.
Oh, that's t, you get to 7,776,000.
7,776,000 million. Put some commas in, makes it easier. So that goes in there, giving us a mass of the planet as 1.6 by 10 to the 31. This is a massive planet, it's bigger than our sun. Okay? We definitely square rooted. Do we have a second on that? Okay, whatever. I just made these values up, so this is not real stuff. Okay? That must be the biggest planet ever.
Is the mass of the star?
Okay.
Oh, it's a mass of a star. Oh, that's okay. Okay, so that's fine then. That's a mass of a star. That's quite a large star. That would be an A at least. Rightio. This time, this one here, I'm not going to do this one because this is one that you have to do on the worksheet. Just to work out what you're doing here, the moon orbits the Earth every 28 days. How far is the Earth from the moon? We need the mass of the central object of the moon's orbit, which is the Earth. The HSC has the mass of the Earth. It's on the back page, it's on the data sheet. So please, when you are doing these type of things, please realise what is on the data sheet. So I'm not going to do this one. So 28 days, we know that that is a lunar month. So you have to convert that into time of seconds. Okay. Right, I wanted to do this one especially because these are becoming more used in the multiple choice. Two planets A and B orbit a star at radiuses r and 1.5 r respectively. The period of A is 5 Earth years, or we just say 5, and the period, we've got to determine the period of B. So, how would we go about doing this? We are not given any values for radius, we haven't given anything for the mass and so on. Okay. So this time we're going to go back to the idea of Kepler saying that r cubed on t squared is a constant for all objects orbiting the same system, same central object of orbit. So looking at just the inner planet here, okay? The inner planet, which we'll say is A, because it's the one at radius of 1 of r, and B is the radius of 1.5, because it does say respectively up there. So, looking at only at A, let's calculate its r cubed on t squared. Well, its r is r, and its period is t. No, sorry, its period is 5, sorry. 5. Okay? So let's put that in for the first one. So it becomes r cubed on 5 squared is equal to k. Are we okay with that? Now looking at the second planet, which is planet B. Now that r, by the way, is the radius of A. So don't forget about that. That r is the radius of orbit of A. The second planet is r cubed on t squared equals k again, because the same object is the centre. For this time, its radius is 1.5, so 1.5 r cubed on t squared would equal k. And remember that that r is the radius of A. Are we okay with that? Now, what can you tell me about this k here and this k here? They're the same. So we're now going to equate them. So popping down the bottom here, that's r cubed on 25 is equal to, what's 1.5 cubed, please? 1.5 cubed equals
3.375.
3.375. So that's 3.375 r cubed over t squared. Are we okay with that? What is common to both sides of this equation? It's the r cubed. Remember that r is the radius of A. And therefore it is the same value on both sides, so it's now going to cancel. That leaves us with an equation which says, that's a 1 up this position here. Multiply this t squared up, you get t squared equals 25 times 3.3375. Multiplying that and taking the square root, we get approximately, is it about 80, square root of 80? Or is it 20? Yes, so 9.2. Is it exactly?
9.185.
Okay, so what's 9.185 or approximately 9.2. Now, 9.2 what? It's years, isn't it? Okay. Because that is in years. And remember, because there is no G over here, there is no M on 4 pi squared. As soon as there is a G, you can't use days, you can't use kilometres. But because we're getting rid of all that stuff and just making it a K, then whatever units we're using, balance on both sides. So this would be Earth years. Okay, how's that? Rightio. I'm just about to hand you out worksheet number 6 for Kepler's Law. So you can continue on that, tick.